Welcome to my YouTube channel. Students, the perfect person does not exist. Everyone has used an eraser. Everyone makes mistakes and no one is perfect. If imperfection really is something we all share, then it should take some pressure off. We don't need to hold ourselves to an expectation that isn't attainable by anyone. In acknowledging this, it opens us up to being more okay to experiment and try. With that positive note, students, let's begin today's session. Today we are going to discuss an experiment so as to draw the current voltage characteristic curve of a PN junction diode during forward biasing. And in the process, students, we are also supposed to determine the value of static and dynamic resistance, right? Before we start, we need to know about the biasing of the junction. Now students, applying an external potential difference on the faces of a junction, that is what we call as the biasing of the junction. And you are already aware, biasing is of two types. One is the forward biasing and the other one is the reverse biasing. Here in this session, we will be discussing the forward biasing characteristic of the junction diode. So in the forward biasing, the P section of the diode is connected to the positive terminal or the higher potential of the external source, while the N section of the diode is connected to the negative terminal or the lower potential of the external source, right? So, in order to perform this particular experiment, we need certain things. We need a junction diode apparatus, we need a junction diode, a source, a resistor, rheostat, a voltmeter, milliammeter, one-way key, then connecting wires or connectors. So these are the things which we will be requiring so as to perform this particular experiment. So let's have a look at the apparatus. This is an apparatus which is used to study the current voltage characteristic curve of a PN junction diode, both in the forward biasing as well as in the reverse biasing. This apparatus is called as Junction Diode Characteristics Apparatus. This is the push button, which is actually the power button. These two actually represent the P sections. Here the connectors are to be attached. This is a diode, and again these two represent the N section. Here again the connectors are to be attached as per the diagram. This is a power supply of range 0 to 1 volt, while this is another power supply of range 0 to 100 volt. Now this is a variable resistor. Now by rotating it in the anti-clockwise direction or in the clockwise direction, the value of resistance in the circuit is altered, and accordingly the different values of voltage and currents can be noted down using this voltmeter and ammeter. This is a voltmeter again having two range. One is from 0 to 100 volt, the other one is from 0 to 1 volt. And this is the switch which can change the range of the voltmeter. For forward biasing, we will make use of 1 volt range. And this is the switch for the changing the range of the ammeter. This is 1000 microampere, and the next one, this is having range of 50 milliampere. So the lower scale, that is from 0 to 50 milliampere, while the upper one, that is from 0 to 1000 microampere. In the case of forward characteristics, we are supposed to make use of the lower scale, which is from 0 to 50 milliampere. Now let's find out the least count. Now students, you can check 10 divisions is equivalent to 10 milliampere. So one small division is equal to 1 milliampere. So the least count of this milliammeter is 1 milliampere. Again, for forward characteristics, we will make use of a voltmeter of range 0 to 1 volt. Now here students, again from 0 to 0.2, there are 10 equal divisions. So one minimum division will have a reading of 0.02 volt, which will be the least count of this voltmeter. Now after the brief description of the apparatus, let us concentrate on the circuit diagram. This is the circuit diagram for the characteristic curve of a junction diode in the forward biasing. Now students, forward biasing we are aware when the P section of the junction diode is connected to the higher potential and the N section of the diode is to be connected to the lower potential of the source, right? And this is the voltmeter which is to be connected across the diode, and this is the milliamp meter which is to be connected in series. The point to be noted over here is during forward biasing, the range of the voltmeter should be from 0 to 1 volt. While on the other hand, we will have to make use of milliamp meter so as to measure the current. One more thing to be noted is that during forward biasing, as you are aware, the thickness of the depletion layer, it decreases. So as a result, what happens is a diode offers low resistance to the flow of current. And students, an ideal diode, it offers no resistance at all to the flow of current. Now we will discuss two terms. One is the static resistance and the other one is the dynamic resistance. Now when we plot graph between different values of voltages and current, the graph obtained would not be a straight line. It will be a curve that we will discuss later on. So what I mean to say is that the PN junction diode, here V and I are not linearly dependent. So it is the case of non-ohmic conductor. So here we make use of two terms. One is the static resistance. This is also known as DC resistance. Static resistance is also known as DC resistance. And it is actually defined as ratio of the forward voltage to the forward current. So static resistance is also known as the DC resistance, and it is simply defined as the ratio of the forward voltage to the forward current. And as the term suggests, it is constant, so it is independent of the applied voltage. In the linear region, this resistance would be constant and it is independent of the applied voltage. While on the other hand, the other term which we use is dynamic resistance. In this experiment, after plotting the IV characteristic curve, we are supposed to determine the value of static and dynamic resistance from the graph. So dynamic resistance is also known as AC resistance. Dynamic resistance, it is also known as AC resistance. And it does depend upon the applied voltage. That's the basic difference. It does not depend upon the applied voltage, it is constant. While dynamic resistance, it does depend upon the applied voltage. So it is defined as the ratio of the small change in the forward voltage to the corresponding small change in the forward current. So that is how we define the static resistance and the dynamic resistance. Now students, let us make use of the actual apparatus so as to realize this circuit diagram and find out the readings for different values of voltages and correspondingly different values of current. Let us make the connections as per the circuit diagram. The P section of the diode is to be connected to the negative terminal of the milliammeter. Now we need to ensure that all the connections which we are using connectors should be tight. Now the positive terminal of the milliammeter is to be connected to the positive terminal of the source. Now the negative terminal of the source is to be connected to the N section of the PN junction diode. So this completes the outer circuit. Now the voltmeter is to be connected across the diode. For that, the N section of the diode is to be connected to the negative terminal of the voltmeter. And the P section of the junction diode is to be connected to the positive terminal of the voltmeter. So that is how the connection is complete for the forward biasing. Students, we have seen how the connections are made in the actual apparatus, right? The positive voltage, it is applied to the diode by a potential divider arrangement, and the forward voltage is kept low. up to a few volts, and a milliammeter is used to measure the forward current. And also we need to remember that we need to start from low voltage and vary it by equal steps. Now we need to record the forward current corresponding to each increment of forward voltage, right? So in the first scenario, when the forward voltage is 0, obviously the forward current is also 0. In the second reading, students, in the beginning what happens is, as the applied forward bias is low, practically no current flows through the junction diode. Now for 0.1 volt, again the corresponding value of the current is found to be 0. If we keep on increasing the forward voltage in equal steps, now for 0.2 volt, again we do not notice any deflection in the milliammeter, so that the forward current is 0. So we can notice that initially, as the applied forward bias is low, practically no current flows through the junction diode. Now students, it is because the potential barrier, it is about 0.3 volt in case of germanium PN junction and about 0.7 volt in case of silicon PN junction. So basically the potential barrier opposes the applied voltage. So in this case also, when we write or rather increase the forward voltage to 0.3 volt, still no current is noticed. It is because the potential barrier, it opposes the applied voltage, right? So therefore, again by increasing by 0.1 volt, now if we consider the forward voltage to be 0.4 volt, now again it comes out to be 0. So students, again I'll repeat this. Initially, as the applied forward bias is low, practically no current flows through the junction diode. Why is it so? Because the potential barrier, it opposes the applied voltage, right? And a small forward current flows till the applied voltage bias does not become greater than the potential barrier voltage. Now basically, if we still increase further the applied voltage and suppose it overcomes the potential barrier, then small current starts flowing through the diode. So now in the next reading, what we observe is corresponding to 0.5 volt, we get a small deflection. It is about 1 milliampere, right? So now it means that a very small current starts flowing through the diode as the applied voltage starts overcoming the potential barrier. Now in this next reading, corresponding to 0.6 volt, the corresponding reading in the milliammeter is found to be 6 units. Now, which suggests that it is 6 milliampere. You must remember the least count of this milliammeter which we are using is 1 milliampere. So 6 divisions, it would be equal to 6 milliampere, right? Now further, we will notice that corresponding to 0.7 volt, the current starts increasing almost linearly with the increase in the applied voltage. Now here it is about 44 units, that is 44 milliampere. So as soon as we notice that as soon as the forward bias becomes greater than that of the potential barrier, the forward current increases almost linearly. Now after the observations, now let's plot the graph so as to represent the IV characteristic of a junction diode during the forward biasing. So here the horizontal axis that represents the forward bias voltage in volts, while the vertical axis, it represents forward current in milliampere. And students, I have considered 1 centimeter along x-axis to be equivalent to 0.1 volt and 1 centimeter along the y-axis to be equal to 10 milliampere. Now initially, as I've stated, now when the applied voltage is less than that of the potential barrier, then the forward current through the diode is almost zero, right? So till 0.4 volt, the current through the diode is zero. So correspondingly, first point is 0, 0, second one is 0.10, third one is 0.20, next is 0.30, then 0.40, right? And then corresponding to 0.5 volt, forward current is 1 milliampere. So corresponding to 0.5 volt, it is 0.1 or rather 1 milliampere, right? Then corresponding to 0.6 volt, the forward current is 6 milliampere. So 0.6 x-axis and y-axis is 6. So this is 5 and this is 6. So this is the point. Then corresponding to 0.7 volt, we have observed the forward current to be 44 milliampere. So corresponding to 0.7 volt, it is 44. So this is the point. Now what we do is, we need to join these points with a free hand. So on joining the points, this is the graph which we obtained during the forward biasing. So it's pretty evident from this graph that VI graph is not a straight line. Actually, it's a curve. It contains a knee. So that is the reason why junction diode is also known as a non-ohmic conductor. So again, I repeat, students, initially when the applied voltage is very low, practically no current flows through the junction diode, right? And once the applied voltage overcomes the potential barrier, or once the applied voltage is greater than that of the potential barrier, then the current increases. And as the forward voltage is increased, the current increases almost linearly, right? But current increases linearly only when the forward bias becomes greater than that of the potential barrier. So basically, students, this point A, suppose this is point A, this point A in the forward characteristic corresponding to the potential barrier appears like a knee, and the forward voltage corresponding to the knee point A is known as the knee voltage. So here knee voltage is 0.6 volt. Again I repeat, students, this point A in the forward characteristic corresponding to the potential barrier appears like a knee. It's a bend, isn't it? And the forward voltage, which is 0.6 volt in this case, corresponding to the knee point A, is known as the knee voltage. Thus, when a PN junction is forward biased, the current increases linearly and rapidly above the knee voltage. It's pretty evident. This is the linear region. Here, the current is increasing linearly and obviously rapidly as well above the knee voltage. And students, the variation in the current with the increase of the forward bias is extremely slow below the knee voltage. Now this is the region below the knee voltage. Here the variation in the current with the increase of the forward voltage is very slow, right? So now let's calculate the static resistance and the dynamic resistance. Now corresponding to point A, the static resistance would be, as I've stated earlier, static resistance is also known as the DC resistance. It doesn't depend upon the applied voltage, right? And it's simply defined as the ratio of the voltage to the current. So corresponding to point A, the voltage is 0.6 volt, while corresponding to point A, the current is 6 milliampere. 6 milliampere. So don't forget to convert milliampere into ampere. So it will be 6 into 10 to minus 3 ampere, right? So R static, that is DC resistance or static resistance, would be given by 0.6 divided by 6 multiplied by 10 raised to power 3. Right? So, if you solve it, it should be equal to 100 ohm. So, this is the value of the static or the DC resistance. Now, let's find out the value of the dynamic resistance. Dynamic resistance, as I've stated, it is also known as the AC resistance. And it is the resistance that depends upon the applied voltage. So in this region, when the curve contains a knee or a bend, here the resistance is not constant. It depends upon the applied voltage. Right? So this resistance depends upon the applied voltage and is defined as the ratio of the small change in the forward voltage to the small change in the forward current. This is known as the dynamic resistance or AC resistance. So RAC or R dynamic, it's given by del V. Let's consider these 2 points. This is point A and suppose this is point A dash. So this contains a knee, isn't it? So we'll calculate the resistance from A dash to A. So it is V2 minus V1, that is voltage at point A is 0.6, voltage at point A dash is 0.5. So we'll get 0.6 minus 0.5 divided by change in the current. Here corresponding to point A, the current is 6 milliampere and here the current is 1 milliampere. So it will be 6 minus 1 milliampere. So don't forget to convert it in amperes. So on solving, what we get is 0.1 divided by 5 into 10 raised to power minus 3. So students, the AC resistance or the dynamic resistance of the diode would be given by, so it will become 10 raised to power 2 divided by 5. So 100 by 5. So that will be 20 ohm. So this is how the static resistance and the dynamic resistance of the diode can be easily obtained using this graph. In practice, a germanium diode is preferred to a silicon diode. It is because in case of germanium diode, the knee voltage is about 0.3 volt, while that of a silicon junction diode, it is about 0.7 volt. So that's the reason we prefer germanium junction diode. So students, that's it. Let us conclude this particular session. I hope you have understood this experiment and do join me in my next lecture then. Thank you.